Okay, first one then, a washing machine washes dirty clothes and then spins the clothes to remove some of the water. Use the correct words from the box. So just underline that to complete the sentence. When the washing machine spins the clothes, something energy is transferred into useful something energy. So there's a big hint there, which one is useful? Well, a washing machine spins clothes. So the useful energy is kinetic. And then it leaves you with, well, what energy does a washing machine use? Well, it's plugged into the mains, so its electrical energy is the input energy. Name one type of energy the washing machine wastes when spinning the clothes. Well, what type of energy does it waste? You could have a couple, but the main one that we always go for is heat energy. And what eventually happens to all this wasted energy? Well, you've got to tick one box. The wasted energy is transferred to the clothes, transferred to the surroundings, or it's trapped and reused. Well, I don't know any situation where a washing machine retraps and reuses wasted heat energy. Wasted energy is transferred to the surroundings. We'll then go down and we're looking at, here a question. Well, the table shows the information about two different washing machines, A and B. Cost to buy, maximum wash load, so how much it can hold, the energy transferred, and the water used in one cycle. Now this question here says one advantage and one disadvantage of washing machine A compared with washing machine B. So the advantage of A. So the first advantage is, what's a good thing about it? Well, it can hold more water, uses less power. It can hold more washing, uses less power and uses less water. So any of those could go into an advantage, a good thing. A disadvantage, a bad thing, there's one clear one. Washing machine A costs more. Then on to question 2. A student investigated the effect of insulation on how quickly hot water cools. And figure 1 is this here. It shows the apparatus that the student used. He added a different number of layers of insulation around each beaker. So he added 3 layers of insulation, 5 layers of insulation, so it's getting thicker, 7 layers of insulation, wrapping it all up in a material. The student measured the temperature of the water every minute for 10 minutes as the water cooled. State one variable the student should control during this investigation. That means, what does he keep the same? In this case, obvious ones, keeps the amount of water the same. He keeps the amount of time that it was left for the same, and that way he can compare how good each of the layers are. Here is our really simple graph. What conclusion should a student make about the effect of number of layers of insulation? So this is about just the number of layers. So I need to look at the number of layers. What does that tell me? What's a clear pattern? The lower down the number of layers, the smaller the temperature. The lower the temperature, sorry. So another way of phrasing it is having less layers means the temperature drops quickly. It's the same for all of them. The more layers, the warmer it is. Okay, back on the other page, there is one anomalous result. Draw a ring around this. Anomalous means it does not fit the pattern. It sticks out. So, for example, if I've got a load of points here on a graph, there's a line of best fit through there. That is my anomalous result. Doesn't fit the pattern. What might the student have done to cause this anomalous result? He might have left it in for a bit longer. He might have misread the thermometer. Something sensible that could be the cause of a mistake. Okay, now here, draw a ring around the correct answer to complete the sentence. Energy is transferred through the wall of the metal beaker by the process of either conduction, convection, or infrared radiation. Conduction is how heat travels through solids. So your clue was the wall. Okay, we're on to a calculation question now. After the water is boiled, the temperature of the water decreases by 22 degrees. The mass of the water in the kettle is 0.5 kilogram. Specific heat capacity of the water is 4,200 joules per kilogram Celsius. Calculate the energy transferred to the surroundings. So I'm going to align the temperature drop or change, mass and energy, specific heat capacity. Okay, so this is where you go to your equation sheet and have a look around. Now we need, if I move this one over here, we need temperature, energy and mass. We've got a big clue here with specific heat capacity, so we're trying to find an equation with that in. So let's have a quick look around down our list. Speed, no. Elastic potential, energy, but no, don't have mass, don't have specific heat capacity. There, I have specific heat capacity. Now let's just double check it's got everything else. Change in thermal energy, oh yeah, change in energy transferred, that's the same thing. Mass of the water and temperature change was the thing just behind over here. Okay, and that's how the equation's written down. So what we'll do is just rewrite that equation there. E equals mass times specific heat capacity times change in temperature. I'll just move that out of the way now. Well, energy is what I'm trying to find out, so I'll leave energy where it is. The mass is 0.5 kilograms. Specific heat capacity is 4,200, and the change in temperature, well, it says decreases by 22. So what I do is times them all together and then work out that answer on my calculator. And the answer is 46,200 joules. All right, part B. Why is the total energy input to the kettle higher than the energy used to heat the water? So why is the total energy in greater than the energy used to heat the water? So does energy absorb to the surroundings, energy is used to heat the kettle, and the kettle is more than 100% efficient? Well, the first port of call is the energy is used to heat the kettle itself as well. Then afterwards, energy would be absorbed away, would be transmitted into the air around and into the surroundings, but firstly, the heat in the kettle. Okay, moving down in. I've got a man in a leaf cutter. The leaf blower is powered by an electric motor connected to a battery. That's an important bit of information. Electric motor connected to a battery. Energy transfers take place when the leaf blower is being used. Use the correct answer from the box to complete each sentence. The battery stores one type of energy. Well, that's going to be chemical. Batteries store chemical energy. The electric motor transfers electrical energy usefully into, well, it's a motor, so it's going to be kinetic energy. And a motor wastes energy as something energy and also heat in the surroundings. So sound energy would be another wasted energy. Moving on to the bottom one. Hardly anyone got this right. In fact, I don't think anybody did. We're working out here the total power input, useful power output, and we want to calculate the efficiency. So the total power into the leaf blower is 750. The useful power out is 360 watts. And you've got to bear in mind that we can't create energy and power out of nothing. So the total amount in is 750. The total power out can never exceed 750. So we've wasted quite a lot. We've wasted 340. 390, sorry. And we've got useful power output of 360. And then we need to remember our equation. Efficiency is the useful power out divided by the total power in. Now, if in doubt and you can't remember that, this number here will always be smaller than this number here. Just check that it's the useful. Yep, and that's the smaller number, so 360 divided by 750 equals, and that's 0.48. Now if you times that by 100, you can get that as a percentage, so 48%. However, either number would be fine, as long as this one doesn't have a percentage written on it. Okay, complete the boxes on the chart to show what happens to energy from the sun. Well, starting off, I've got 100 units of energy from the sun. And if I have a look just over here, 30 of that goes to the atmosphere, 50 passes through the atmosphere. So what have I got left over? I've got 20. Now, onto this next box. I've got 6 to heat the atmosphere, 24 energy drives the water cycle, and a certain amount of energy heating the Earth's surface. Well, what should that add up to? Well, that should add up to this answer here. So, 24 plus 6 makes 30. That leaves 20 from that 50. And then we're on to the final one here, to outer space, to the atmosphere. Well, if I've started off with 20 joules, I've got 14 there, I must have 6 there. Okay, units, joules for work done, meters for distance, newtons for force. Okay, we're on to question 7. A householder wants to reduce her energy bills. She collected information about a number of ways of reducing energy used, and this information's here. So we've got installing an energy efficient boiler, insulating the loft, installing double glazing in the windows, installing cavity wall insulation. This is the cost to buy it, 2,000, 400 for the loft, 12,000 and 415. And that's the money saved per year. And that's important there, it's per year you save it. So we've got to use this table to compare the different ways, and we should include some calculations. Okay, we could start off and get some of our 6 marks here by looking at some simple comparisons. Well, looking at the money saved per year, an energy efficient boiler seems to be best because you save £320 per year. The worst seems to be double glazing. But in terms of cost, insulating the loft is very cheap, with double glazing the most expensive. So simple statements like that are fine. But if you're going to do a calculation, what you want to be thinking of, and the easiest one to see here, is the loft. If I pay £400 and I save £200 per year, how much? So we do 400 divided by 200, as in, and this will give you how many years it takes to pay that back. Well, 400 divided by 200, 4 divided by 2 equals 2 years. And that's something called the payback time. And it's a way of comparing which one was the most cost effective. Because if you look at installing double glazing, £12,000, and you save £120, that would take you 100 years to pay it back. Now, if you went through that for all of them, you could then make a comparison statement and finish up with, so I would choose. And I think the most obvious one in all cases is insulate the loft, but as long as you justify it. Right, okay, moving on to the next one. Increasing the amount of insulation in a house affects the total U value of the house. What is meant by the term U value? It's basically a measurement for how good an insulator is. How is U value affected by increasing the amount of insulation? If you have more insulation, the U value becomes lower, because what the U value is telling you is how much energy is lost per metre squared of material for one particular metre thickness. So if you increase the amount of insulation, you lose less energy, and so your U value drops. Okay, moving on to question 8. Solar energy is a renewable source. What is meant by renewable? It means it is replenished quickly. And what that means is it forms new fuel quickly. Well, wind is constantly being replenished by the sun. Solar, again, constantly being replenished, but fossil fuels will run out. So fossil fuels take about millions of years to form. So that's not renewable. So renewable means it isn't used up, or it's replenished or replaced quickly. Two of the renewables, the easiest ones would be wind and solar. You could have many others such as geothermal, such as tidal, wave power, or so on. Okay. Right, this question here was a 2-mark question. Use the data on the table to describe how the average energy input to the solar cells depends on the angle of tilt. And if you look at the top of the bit that I didn't read, the table gives the average energy input each second to a 1 metre squared area of solar cell for different months of the year. Right, so how does the average energy input depend on tilt? Well, if this is the energy input, then let's have a look at all of them. We seem to have a maximum at 30 degrees. So you get most of your energy out when it's at 30 degrees. That would be 1 mark there for saying 30 degrees is a maximum. You then need to say something else. So angles greater than 30 degrees, it appears to drop. So 2 points. 1 for saying 30 is the max. And 1, what happens now? What's the rest of the pattern after the energy starts to decrease? Okay, moving on now to this one. I've got a bit of a calculation to do. The total area of the solar cell panels used by the householder is 5 metres squared. The efficiency of the solar cells is 0.18. Calculate the maximum electrical energy available from the solar cell panels in June. So let's have a quick look at these. So efficiency is 0.18, 5 metres squared. I need to go back and have a look at this graph, the table. Okay, and I've taken this from the previous page. So now what we need to do is work out the maximum energy produced. Well, the first thing is if it's only 0.18 efficient, that would actually equal 18%, but we're not going to do anything with the percentage for this. In June, the maximum was 720. So what I want to know is what is 18% of 720? Well, what you do is you just times it by 0.18. So 720 times 0.18 equals 129.6 joules every single second. And then you've got to bear in mind that it was 5 metres squared. Now the previous question was for just 1 metre squared. So we times that by 5, gets us an answer of 468. But the first thing we needed to do was to actually just calculate the efficiency. So the decimal value for efficiency multiplied by the maximum. And then we just times that by 5. Okay, we're now on to National Grid. Right, most people got this answer. Even though the householder uses solar cells to generate electricity for his home, the home stays connected to the national grid. You have one reason why the householder should stay connected to the national grid. Well, if he's using solar cells, they're not going to be reliable all the time, I don't think. So, in other words, it might be cloudy and we need to draw electricity from the national grid. So something that says that solar cells aren't reliable. Final thing, a step-up transformer increases the efficiency of the national grid. Explain how. You either know this or you don't, to be honest. A step-up transformer increases the voltage or potential difference across the wires. And if it pushes up the potential difference, then the current decreases. And the reason for that is this equation here. Power is current times potential difference. So if the power generated and transferred across the lines stays the same, I'm not going to change the power. What I can do is I can either have a very big voltage and a small current, or I could have a very big current and a small voltage. Now if you choose this option here, high voltage, small current to get that same power, what that means is the wires don't get as hot, so you get less energy lost as heat. Hence, it's more efficient. Okay, water falling through these turbines. I've got this reservoir here. The movement of the turbines causes electrical generators to generate electrical energy. Water goes through there, spins those. What we then need to do is this question here. Write the equation which links kinetic energy, mass and speed. Kinetic energy is half times mass times speed squared. So what we're now going to do is put that in place for this question here. In 1 minute, a mass of 9,000 kilograms flows through the turbine. The speed is 30 meters per second. Calculate the total kinetic energy in that 1 minute. So, checking my numbers, 9,000. Oops, let me just get rid of that. 9,000, 30 meters per second. Calculate the total kinetic energy. Let's put the numbers in place. Equals a half. That's a constant times 9,000 times 30 squared. Now on my calculator, I always do the 30 squared first. So that is 900 times the 9,000, oh, write that down wrong, times the 9,000 from the mass, times a half, gets us my energy, so times 9,000 gets me 405,000, as in 4,050,000 joules. The problem is though, I've got an answer that needs to be in kilojoules. Now kilo, this little k here, means 1,000. So what we're going to do then is divide that by 1,000. Now simply you just cancel off those 3. So your answer is 4,050 kilojoules. Okay, right, now then, the rest of the mark scheme is at the end of this page, at the end of this video, so I'm going to scoot through now in a minute, and you can pause it and look at those answers to help you out, so we'll go through now.